Hello everyone. In this video we're going to do an AP Physics B problem. The AP Physics B was the old AP Physics exam. And this is question 2 of the 2002 exam form B. So one of the free response questions. So let's read the question. A ball attached to a string of length L swings in a horizontal circle as shown above with a constant speed. The string makes an angle theta with the vertical, and T is the magnitude of the tension in the string. Express your answers to the following in terms of given quantities and fundamental constants. Okay, so part A. Draw and label vectors to represent all the forces acting on the ball when it is at the position shown in the diagram. The lengths of the vectors should be consistent with the relative magnitudes of the forces. Alright, so assuming it's on Earth, which it possibly is, there will be gravity. Just a minute. Right? There will be gravity like this, right? So some mass m, they don't give us m, so not mg. Let's just call this fg to be on the safe side. So fg, the force of gravity, right? Then this would be tension T. So they give us T. And are there any other forces? Well, there isn't any other actual forces. So this will be it. These are both the forces. So, part B. Determine the mass of the ball. Okay, so we're not given the mass, but we are given the tension. So what we can do, well, they tell us usually not to draw on the diagram, so I'll draw another diagram over here. They tell us, so this is T, this is some mass, mg, all right, so Fg equals mg. Now let's divide the tension force into components, all right? So I'm going to draw here as well. So let's just draw here. Alright, so let's divide it up into vertical and horizontal components. So this is Tx, this is Ty, right? Well, since this and this are both vertical, these both have to be parallel. So by the alternate interior angles, these angles must be congruent. So Ty will equal T times the cosine of theta. Ty will be T times the cosine of theta. Okay, and since Ty must equal Tmg, sorry about that, so net force Y equals 0. That means Ty, which is, we just said it was T cosine theta, right? Because if you bring, right, if you have, T and Ty over here, you can just shift this like this, right? And this will be your angle, because we said this will be the angle and these are both parallel, okay? And then you could easily see from trigonometry that Ty will be T cosine theta. So that's where I got that from. So T cosine theta minus mg will equal 0. That means mg equals T cosine theta. And the mass of the ball, m, is T cosine theta over g. All right, so far we've followed the rules. We've fixed everything's in T, theta, and a physical constant, g. Okay. So part C, determine the speed of the ball. Okay, so this is where like some centripetal force stuff gets in. Right? So if the ball is moving in a horizontal circle, there should be a component of the force that should be keeping it in a horizontal circle. So either be pointing toward or away the circle. And if it's moving in uniform circular motion, there should be at least one force moving inside the circle. So if you look at the diagram here, you can see that TX, the horizontal component of the tension, which is T sine theta, if you look at our little triangle here, right? That is the centripetal force. It's keeping the ball in a circle. It's pointing inside the horizontal circle. So Tx is equal to Fc. Okay? So Tx is Fc. That means T sine theta will equal, well, mass times acceleration. So m times centripetal acceleration, v squared over r. And we just found out that the mass is t cosine theta over g. Let me just erase. Okay, so t cosine theta over g times v squared over r. So right then and there, you can notice that the t's will cancel. And you're left with sine theta equals v squared cosine theta over rg. Rg. Okay. So what if you divided both sides by cosine theta? Right? And then we're left with sine theta over cosine theta equals v squared over rg. Okay. So what's sine theta over cosine theta? Well, you could prove this if you want. That will equal tangent of theta. Right? So let's just prove it right now. Just pretend you got this right triangle, right? This is A, this is B, this is C, this is your angle theta. The sine theta be opposite over hypotenuse, so B over C. Cosine of theta will be adjacent over hypotenuse, A over C. And tangent of theta will be opposite over adjacent, B over A. So if you were to divide both the sine theta divided by cosine theta, you get sine theta over cosine theta, right? You get B over C over A over C. And if you multiply by the reciprocals, you get B over A. And that is tangent of theta. So let's replace this by tangent of theta. So v squared over rg. And then if you multiply both sides by rg, we get v squared equals rg tangent theta. And v equals square root rg tangent theta. Okay? So we might, well, we're done, but we're actually not done. You see, they don't give us r, so we need to find r. However, it's not that simple. I'm going to draw in red here, okay? So let's think about the right triangle I'm going to draw in red. Right? Where this is r. They give us L, right? So let's express R in terms of L, because L is the only length that is given here. So So, sorry about that. So, L is the only length that is given here. So, if you look at the triangle, well, theta, R is opposite of theta, and L is the hypotenuse. You could just use sine. So, sine theta equals R over L. However, we have that R equals L sine theta. I'm just drawing in red. So it corresponds to that triangle. So we get V equals square root of LG sine theta. So L sine theta times G times tangent of theta. All right. And that is it. So now everything's in terms of L and theta, and we're given L, so it checks out. Now D is the hard part. Well, not really that hard. It's not really hard at all. Determine the frequency of revolution of the ball. Okay, so frequency is defined as the number of cycles per second. So specifically, how many cycles does the ball do in, how many cycles does the ball go in 1 second, right? So frequency is 1 over the period, right? Frequency is defined as 1 over the period. Period is how long does it take to do 1 cycle? And if you take the inverse of that, that's frequency. Okay, so let's first find the period, and then we can take the inverse of that right afterward, and that'll give us frequency. So period, well, there's no efficient way to find period unless you, well, there is an efficient way to find period. Sorry about that. So there is an efficient way, and that involves finding the distance traveled in 1 cycle divided by t, right? So the way you can find the period is use the general definition of velocity, delta x over delta t. What's delta x in 1 period? The distance in 1 period, that'll be 2 pi r over t. And we know that r is L sine theta. So 2 pi L sine theta over t. Okay, so t is equal to 2 pi L sine theta over v. And if we substitute our expression for v, we have 2 pi L sine theta over square root LG sine theta tangent of theta. Okay. So if you just take the reciprocal of this, they'll accept it, and this is a non-simplified answer. If you take the reciprocal of this is just the period we found. So if you flip this and make the square root on the top and 2 pi L on the bottom, that'll give you your frequency. But let's simplify this, because this can be simplified. And I'm going to show you how. So what we're going to do to get rid of that radical, you could either choose to rationalize the denominator. You can rationalize the denominator, or since there's a lot of stuff in that denominator, we're just going to square both sides instead. So t squared, we're still solving for period. So I want to solve for period. So once you get a simplified period, you can just get a reciprocal of that and find the frequency. So what I'm going to do is square both sides. So that's 4 pi squared L squared sine of theta squared, or sine squared theta equals LG sine theta tangent theta. Okay, so now you can immediately see This cancels out the square. This cancels out this square. And we're left with 4 pi squared L sine theta over G tangent of theta. So if you take the square root, you get t equals square root 4 pi squared L sine theta G tangent of theta. Okay, so we can do some more simplification here. So you could easily pull out 2 pi. Pi squared is a perfect square, 4 is a perfect square. So you could pull out 2 pi out of the radical. Okay, so we're left with L sine theta over G tangent of theta. So you have sine theta and tangent theta, and they're related by the fact that sine over cosine is tangent. Sine theta over cosine theta equals tangent of theta. Okay. So if you solve for sine theta, I guess sine theta equals tangent theta times cosine theta. 2 pi times L tangent theta cosine theta over G tangent theta. And why did I do that? Because see, look at it. This cancels out with that. So tangents cancel out, and we're left with our simplified period. 2 pi L cosine theta over G. But we need to find the frequency of revolution of the ball. So the way we can do that is we could just take the reciprocal. F equals 1 over T equals 1 over 2 pi square root L cosine theta over G. Okay, so that equals 1 over 2 pi times the square root of G over L cosine theta. That is its most simplified form. You cannot simplify it more than that. So this is at its most basic. This is the frequency of revolution of the ball. Okay, so part E. So suppose the string breaks as the ball swings in its circular path. Qualitatively describe the trajectory of the ball after the string breaks, but before it hits the ground. So they're asking us to, like, pretend the string broke right here. Okay? Now, from uniform circular motion, if the string breaks, you lose your tension force. That means you lose your centripetal force. Okay? So the ball will keep on moving in the tangential velocity, like this, before it falls to the ground. So it'll keep on moving like this. It will not like keep on moving in a circle because there's no centripetal force keeping it in a circle. So it will keep on moving straight in the direction of the tangential velocity before it strikes the ground. So that's part E. So I can't really write it because as you can see, my space is pretty much occupied. So yeah, so it will keep on moving in the direction of its tangential velocity right before the string broke, and it'll keep on moving down like a projectile, a horizontally launched projectile. Okay, so we just finished this question. If you have any questions, this was a pretty hard problem. Okay, I had trouble with it when I first solved it, but it just some algebra. You could have saved a lot of time by just taking the reciprocal of this step over here. So you saved a lot of time just taking the reciprocal of this step over here. Just 1 over that would have given you the frequency, but just to show you how to simplify, they also took this as an answer, well, the inverse of this as an answer, and they took this as an answer. Okay, so Yeah, so that's basically how you do this problem. So if you have any questions, just comment below and see you next time.